Ladies and gentlemen, welcome to the last video in the topic of engineering dynamics and specifically about the introduction to rotor dynamics. In the last videos, we got the equations of motion for a system like this. Then we talked about a rotor with symmetric bearing stiffness, about the eigenfrequencies. Then we got a response, or the amplitude response, or better to say the frequency response function of our system with a unbalanced mass. And now we're interested, well, what if we're not having a unbalanced mass, but we're actually exciting our system periodically, what will our system do? So we talked about the gyroscopic moments, we got the equations of motion, this is our equations of motion, we got our eigenvalues, we talked about the Campbell diagram, this is the response to an unbalanced mass, where we had the frequency function right here. And now we're talking about a response to external forces. So we have now the same stuff that we had before. We're saying that Kx and Ky are equal because then it's easier for us. And the forces now, the external forces, are now a periodic excitation force. So this is something like a shaker that will shake our system or apply a periodic force in direction of x. And the solution of our system we propose as xy times cosine excitation times t and ay times sinus omega excitation t. So now we have two omegas, and we don't need we must not confuse them. So once we have the rotation speed, and once we have the rotation speed, and the other time we have omega as our excitation frequency. So omega x and omega are not related. The solution of our system, this is our equation of motion. We know that y is 0, and it will leave us with these two equations. And now we can actually, just because we have two equations and two unknowns, we have xy and we have ay and ax, we can just solve directly for ax and ay. So these are our response amplitudes. So we can do a little simplification from these two matrices where we remove the cosine, and the cosine, and we remove the sine and the sine right here. And we get our little mass dash, where we have mass plus the rotational, plus the inertia around z and y. And we are left with these two equations. And solving them for ax and ay, we will get these two equations. And the most important part for us is the amplitude in x, because we're exciting into the x direction, because we're shaking that system from the x direction. We also know, well, how does the system respond? And for that, again, we draw the frequency response function. So we have the harmonic excitation. So this is our shaker with the excitation frequency omega x. And we will get, or let's look at this first, we will get two resonances. So one, we start at close to 0. Then we go up to our first resonance where we hit the backwards whirl. Then we go down almost to 0. Then we go back up again, hit our forward whirl, and go to 0. This will actually lead us to 0. And the interesting part is that if we tilt our Campbell diagram, so this was our backwards whirl, and this was our forward whirl, and we have a certain excitation speed, our rotation speed, we will hit the eigenfrequencies exactly at this point where these two lines intercept. So our rotation speed is equal to our eigenfrequencies. And this will get us the backwards whirl and the forwards whirl. But the most important part, or the most interesting part, is this value right here. So what happens if resonance is easy to understand. So this amplitude goes to infinity and this amplitude also goes to infinity. But what is happening right here? How can a system that even if we're exciting it in the x direction, not move into the x direction? Well, this part is because we have those gyroscopic moments. Let's look at them right at the beginning. So we have those gyroscopic moments. And what they actually do is, let's look at the first picture again. And what they actually do is, this is the part that we talked about in the first video, that there is a certain frequency or excitation frequency coupled with the right rotation frequency, that if we're trying to push our rotor in the x direction, it will actually just move up. And if it moves up, it will then try to move in the other direction. But the force, the excitation force, will cancel the force or the moment of our gyroscopic moments. So the force of the excitation force and of the gyroscopic moments will cancel each other out. And in this scenario, our system moves only up and down in the y direction. So this is basically, again, the same thing that where we had the frequency, or the where we had two degrees of freedom, and 1 degree of freedom stays constant, while the other one is taking all the movement. And this is exactly the thing that is happening here. If we're pushing it in the x direction, it will move up into the y direction and try to move again, because it moves up into the y direction, into the x direction. But this movement again is basically stopped by the excitation force of our external force. And because this is happening, our system will just move up and down. Let's summarize what we talked about. So we have a rotor that we apply a periodic force, and we will get, we propose a system where we have amplitude in x, or a solution amplitude in x and amplitude in y. We say that kx and ky are equal, and we get these two equations. We remove the sine, the cosine, and the cosine here, and get these two equations. We solve them for x and y because we have two equations and two unknowns, and then we can plot the frequency response function of our response into x. And we're actually hitting both eigenfrequencies, so both eigenfrequencies. So we have resonance at the forward whirl eigenfrequency, and we have resonance, this is the backwards whirl, and this is the forward whirl. And the most important part not to forget is that there is a frequency where the excitation frequency for a specific rotation speed is just such that our system is not moving into the x direction, because the gyroscopic moments and the forces from our excitation cancel each other out. If you have any questions, feel free to ask them in the comments down below. I hope this video gave you a better understanding of the topic of rotor dynamics. Thank you very much for your attention, and I'll see you next time.